We now know that time elapses more slowly on a clock that is moving relative to you. And we're going to shortly calculate the rate at which that moving clock ticks off time compared to your clock. But first, I want to address two vital questions to this issue of the slowing of time. And the first is, if you are moving with that moving clock and someone on the platform watching you says that your clock is ticking off time more slowly, do you feel that time is elapsing more slowly? And the answer to that is absolutely no. You don't, because again, it goes back to that very same point that I stressed at the outset, right? When we had, say, George and Gracie out there in space. So they're out there in space and they were passing each other, and I emphasized that each could claim to be at rest and that the other is moving by them, right? So that very same idea here, we're only talking about constant velocity motion, fixed speed in a fixed direction. That tells us that the person that you see moving with that moving clock, that person can claim that they are at rest, and it's you that's moving. So from their perspective, time is elapsing as it always does. If you will, the light clock relative to them is going up and down, just as it always does. You and the rest of the world are rushing by them. So, bottom line is, nobody actually feels internally that time is ticking off more slowly because of the fact that everybody can claim to be the person, the clock, at rest. Okay, now, that being said, if indeed you are watching a clock that relative to you is moving, you should see that time on it is elapsing more slowly if you're not moving with that clock. So the question then is, why don't we ever notice that time ticks off slowly on a clock that's moving relative to us? Why did it take the genius of Einstein to figure this out? Why don't we know this in our bones? Why don't we experience this in everyday life? And the answer to that is the same answer that we've come to in analogous questions that we've encountered earlier. It all has to do with the fact that everyday experience only taps into a small little part of how the world is configured. And in this particular case, everyday experience does not involve us watching objects that attain speeds near the speed of light, which is where these effects kick in maximally. So let me just give you a little demonstration where you can see that idea in action. So this here is, if you will, your very own light clock that you can play with on your own. And what you do with this light clock is you set the velocity of the clock at whatever value you want, and it's all in fractions of the speed of light. Good. Okay. Now, if you set the speed of the clock to be relatively small, non-zero but relatively small, let's look at the rate of ticking on that clock compared to what it would be doing if the clock were not moving at all. And notice that the diagonal path here has hardly any diagonal to it at all, because the speed of the clock is so slow compared to the speed of light that light goes up and down with virtually no ability for the clock to move to the right during any of the tick-tocks. So the motion of the clock has very little effect on the passage of time when the speeds are slow. But when the speeds pick up, let's do another version of this. Let's put the speed, 60% or so of the speed of light. Now, the clock can move significantly between its tick-tock because it's going quickly. It's going at a speed on par with the speed of light, half the speed of light, a little bit more. And now the diagonals truly are longer than the straight up and down. And just to emphasize that point maximally in this little demonstration, again, play with this. Here we are at 99.9% of the speed of light. So if I now turn this fella on here, wow, look at that. Look how far. It didn't even get to do its first tick of tick-tock. That's how fast this clock was moving relative to the speed of light. So whereas when it's stationary, it would go tick-tock, this one went tick. Didn't even get to the k of tick. That's how far this clock moved to the left because of its very high speed. So this clearly shows us that, again, it is the speed of the clock which determines the rate at which time on it will tick off more slowly than on a clock that is stationary. That's the key point. But we want to go further, because ultimately what we really want to do is to derive a formula for how much slower time ticks off on a moving clock compared to a stationary one. And I'll derive that mathematically for those of you who are taking the math version of this course in the next section. But let me give you the essential idea here. And what is the essential idea? Well, the essential idea can be gotten by a little bit of analysis on one of these moving light clocks. So here is our little schematic version of a light clock that's in motion. And if you think about the process of going tick-tock, based on what we've described in that little demonstration that we just did, the key thing to think about in order to know how quickly this clock will go tick-tock is to look at the length of the trajectory. So the light, little photon, if you will, starts here, and in order to go tick, it has to travel that journey, and to go tock, it has to travel that journey. And since the speed of light is constant, what is most relevant here is how long that journey is relative to how long that journey would be for the stationary clock. And for the stationary clock, it just goes up and down. So if I just mark that for good measure, let's give that guy a different color. Let's call this guy blue. So if this length over here is, say, equal to L, and this length over here is equal to D, then this one will be D as well. So this guy, to go tick-tock, the stationary one, it goes up and down, so it goes L plus L. It goes 2L to go tick-tock on the stationary clock. And on the moving, to go tick-tock, it's D plus D equals 2D. Now, again, since the speed of light is constant, this is telling us that the duration for each tick-tock on the moving clock, let's compare that with the duration for this guy to go tick-tock on the stationary. So that's the duration of tick-tock on the moving compared to the duration for tick-tock on the stationary clock. Well, that ratio is just the ratio of the distances, because the speed of light is the same. So that's 2D over 2L, which is D over L. So that is the essence of the issue. Tick-tock on the moving clock compared to tick-tock on the stationary clock is the ratio of the length of the trajectory in the moving clock from our perspective watching it compared to the length of the trajectory on the stationary clock. So that is the key formula describing the rate at which the tick-tocks happen on the two clocks. But now let me just take this a little bit further and note the following point, which easily can get confusing. It's a very simple point, so if ever you find yourself confused in this, calm down, take a deep breath, think it through, and you'll be able to work it out, which is this. If you're considering the amount of time that elapses between two events, right? If you're measuring the elapsed time between two events on any clock, but in particular on a light clock, you want to know the number of tick-tocks. That tells you how much time has gone by. Now, if the duration for each tick-tock is longer, then less time will elapse on that clock. Longer tick-tocks, tick-tock, means less time will elapse. So what that means is, if we are looking at not the duration of tick-tocks, but the elapsed time, so the elapsed time on, and I'll fill in which clock in a minute, divided by the elapsed time here, and I'll fill in the clocks right now. So if the duration of the tick-tock on a moving clock compared to the duration of tick-tock on a stationary clock, let's say this is a ratio of 5 to 1. That means that 5 times more time will elapse on the stationary clock, where the tick-tocks are faster, compared to the amount of time that elapses on the moving clock. So then this translates into the elapsed time on the stationary clock compared to the elapsed time on the moving. These are inversely related to the duration of the tick-tocks. This is equal to d over L. So again, if this length here is 5 times the length for the ball to go up and down, the ball of light to go up and down in the stationary clock, then that means the tick-tocks are happening 5 times as slow in the moving clock, which means 5 times more time will elapse on the stationary clock compared to the moving clock, because the tick-tocks are happening faster over here. So that means that we can now take the little formula that we have indicated over here and translate that into the elapsed time in the stationary clock to the elapsed time in the moving clock is the ratio of the length of that diagonal that we have over here to the length of the straight up and down. So now we've basically reduced the calculation of how much time slows on the moving clock compared to a stationary clock to really a bit of geometry and trigonometry. And I'll show you how that goes if you're taking the math version in the next section, but let me give you the answer. Here is the answer that we will establish. If this clock that we are looking at over here, let's say this guy has a velocity that's heading over this way, and this velocity is equal to v, then that formula takes the speed v as input and tells us how much slower time elapses on the moving clock compared to the stationary clock. Now, for those not taking the math version of this course, this is one of only 2 equations I'm going to show you. The other, of course, being E equals mc squared. But this formula is just as important as E equals mc squared, not quite as famous, but it tells us that the time that elapses on a moving clock is slow relative to that on a stationary clock by a factor of 1 over the square root of 1 minus v over c squared. This expression, this little formula, is so important, we give it its own name. We call it gamma. Again, we'll derive that in the next section, but I just want you to get a bit of a feel for this result before we do that. We are going to look at 2 clocks, and one clock you can imagine is here on Earth, which we will call the stationary one. One clock is on a rocket ship, so now we've gone from a train to a rocket ship, because we want some of these speeds to be able to be really fast. And what this demonstration will do, it simply takes the formula that I have told you that we will derive in just a moment. So just remember what that formula is. So this is equal to, we claim, 1 over the square root of 1 minus v over c squared. The demonstration will take the v that you input into the demonstration, calculate that, and show us the amount of time that elapses on the rocket compared to the amount of time that elapses on Earth. Okay, let's do that. All right, so let's be conservative at first. I've chosen the speed of the rocket ship to be 12% of the speed of light. Set this guy in motion, and you can begin to see a bit of a time difference between them. It's hard to see, but there is a bit of a difference. But now let's crank this up, and let's go to 66, 67% of the speed of light. And now you really can begin to see that the elapsed time on the rocket ship is less from the perspective of those of us here on Earth looking at our stationary clock. And let's then be inspired, and you should do this on your own, again, to feel the formula, this formula for this object called gamma in your bones. I'm now at 95, I don't know, let me push it all the way. Let's go to 98.5% of the speed of light. And now you really begin to see the difference between these two. It's dramatic. Here we are on Earth, and hour after hour is going by in the usual way, but from our view, that clock in motion, time is ticking off very, very slowly. So this factor, this guy called gamma, this time dilation, as we call it, kicks in substantially for speeds near the speed of light. At everyday speeds, time dilation is still there, right? So this guy over here, where the velocity is in the denominator, that kicks in at any velocity, right? But that number is so close to 1 for pedestrian everyday speeds that we don't notice it. So clocks move around the world all the time. We don't notice that they're ticking off time at a different rate, only because that formula is such that gamma is very, very close to 1. So the ratio of time on the moving clock to time on the stationary is virtually indistinguishable from being equal to one another. But the effect is there nevertheless. Having said that, let me just emphasize one little loophole that we will come back to. It's kind of a curious loophole, which is that if you have individuals that are moving at relatively slow speeds, but they're very, very, very far apart, then that can amplify this effect. So there can be big differences in time, even at slow speeds, if you're talking about observers that are very far apart in space. We will come back to that and its curious implications as we go forward. But putting that to the side, if you're talking about observers that are reasonable distances apart, distances that might be planetary scales or even galactic scales, it's only when they're moving relative to one another very quickly that this time dilation effect kicks in substantially. But it is there all the time. So in some sense, we all carry our own time. This completely shatters the oneness of time that Newton envisioned, right? Newton envisioned that there's one clock out there in the cosmos ticking off second after second after second, the same for all of us. This shows directly that that's not true. We each carry our own clock, and our clock ticks off time at a rate compared to others that depends on the relative speed between us.